Welcome to This Explainer. Today, we're unraveling the hidden engineering mysteries behind how we actually measure massive amounts of electrical power in the lab without, blowing things up. If you've ever wondered how engineers manage to tame the raw, invisible power flowing all around us, you are absolutely in the right place.
I mean, think about those massive transmission lines humming above your street, or the heavy main feeds powering an entire industrial plant. How on earth do you safely measure something crazy like 5,000 amps of electricity without completely melting your tools, or worse, yourself? To start our investigation, we really have to look at the immense danger of raw power and the ingenious little devices engineers use to tame it before it ever reaches a standard meter.
Okay, let's jump right into Section 1, stepping down massive currents.
So, our journey begins up on those high-voltage transmission lines. Trying to measure that current directly, it's basically physically impossible. If you hooked up a standard lab meter straight to a city power line, it would literally vaporize in a millisecond. To get around this, engineers use what's called a current transformer, or a CT. It's a special instrument transformer designed to produce a safe, alternating current in a secondary winding, and that current is perfectly proportional to the massive surge happening in the primary line. Essentially, it safely steps thousands of amps way down to a standard output of just 1 or 5 amps, something a normal off-the-shelf ammeter can safely read. Out in the real world, you'll see these in a few different shapes. You got wound, toroidal, and bar type, but honestly, no matter the physical shape, they all do the exact same crucial job. They rely on magnetic flux to safely isolate your delicate instruments from the terrifying high-voltage power lines. Sometimes a heavy-duty cable is wrapped around a core, or, like with the toroidal type, the live wire is simply threaded right through a central window. Which brings us to Section 2, the open circuit danger.
Now, these transformers might seem perfectly safe, and they are, mostly, but they actually hide a seriously counterintuitive secret. Every electrical engineering student learns this very quickly. What actually happens if you just remove the ammeter from the circuit? Say you're done taking your readings, so you just unplug the meter. It seems totally harmless, right? But disconnecting the measuring device from an energized current transformer unleashes a massive mathematical and physical nightmare.
Because the transformer's coils act in reverse, due to what we call an inverse turns ratio, an open-circuited secondary suddenly turns this safety device into a massive step-up transformer. We're talking instant, lethal induced voltages. Imagine a spike hitting 76.8 kilovolts just because you unplugged a simple meter. The core magnetically saturates, and with no opposing secondary current to keep things balanced, boom, the voltage skyrockets to deadly levels.
So how do engineers solve this deadly little trap and stop equipment from exploding? They have one absolute, golden rule. You must always intentionally short-circuit the secondary terminals before removing the load. I know, it sounds totally backward. Normally, a short circuit is exactly what causes fires, but with a current transformer, a short circuit is exactly what keeps that voltage at zero and keeps you perfectly safe.
Moving right along, here is Section 3, Anatomy of a Wattmeter.
All right, now that we've safely stepped that massive current down, let's zoom in a bit. Let's look at the benchtop tools we use to measure actual power consumption, like the classic wattmeter. These work on the electrodynamometer principle, and the internal mechanics are just fascinating. Inside, you've got a fixed current coil connected in series with the load, and a moving voltage, or pressure, coil connected in parallel. As power flows, their interacting magnetic fields physically push a pointer across a dial to show you the real power being consumed.
But here's the thing, as a user, you aren't messing around directly with those internal coils. Externally, you're interacting with 4 very specific terminals. M for the main side, L for the load side, C for the common junction, and V for the voltage or negative terminal. Lock those letters into your brain for a second because they set up our next big engineering puzzle.
And that is Section 4, the missing internal connection.
This brings us to a really weird design quirk. At first glance, it honestly looks like a manufacturer's mistake, but it's actually an intentional stroke of genius. For almost every practical, everyday setup to measure standard single-phase power, you have to manually bridge the mains and common terminals, M and C, with a physical piece of wire yourself. Without that external bridge, your meter literally does absolutely nothing.
So you've got to wonder, if these two terminals basically always need to be connected to get a normal reading, why on earth didn't the manufacturer just connect M and C internally at the factory? Why intentionally leave them physically separated on the outside of the casing and make the user do the extra work?
Well, it turns out keeping them separate gives engineers a total diagnostic superpower. By leaving them unlinked, you can actually isolate the current coil to run what's called a creeping test. That's where you check if the meter's disk is falsely rotating just from the voltage field alone, even when absolutely zero power is being drawn. Plus, separating them unlocks some highly specialized setups, like measuring reactive power across complex three-phase loads, which requires tapping into completely different voltage lines.
Which leads perfectly into Section 5, phantom loading and calibration.
But honestly, the most brilliant reason for this missing internal connection comes down to simple economics and heat management during calibration. Let's say you need to test if a 220-volt 5-amp watt meter is perfectly accurate. If you test that on a real physical load of full capacity, you are wasting over 1,000 watts of power as pure heat. That's basically running a heavy-duty space heater for no reason, and that heat can actually warp your delicate test results. But by separating the M and C terminals, engineers invented a clever workaround called phantom loading, which drops that wasted power down to just 50 watts.
So, how exactly does this phantom magic trick work? It's incredibly clever. First, you make sure those M and C terminals are completely separated. Next, you feed the pressure coil the full rated 220 volts. Finally, since the current coil has super low resistance, you just feed it with a tiny, isolated 10-volt source, just enough electrical push to drive the 5 amps of current you need. By driving that tiny separate voltage source through just the current coil, the watt meter is essentially tricked into thinking it's reading a massive load. You get a perfect calibration test, but you slash the energy waste and keep everything nice and cool. When you actually map all of this out in a real lab calibration circuit, you can see how all these distinct modular pieces, the transformers, the voltmeters, the ammeters, and the separate power paths, they all fit together like a giant puzzle. And this intricate, highly controlled testing environment is absolutely only possible because those internal watt-meter coils are intentionally disconnected by default.
From using clever illusions like phantom loading to save energy, all the way to intentionally short-circuiting live wires just to avoid getting hit by a lethal 76 kilovolt shock, it really does change how you look at the grid, doesn't it? It kind of makes you wonder, what other invisible engineering secrets and high-stakes mathematical puzzles are silently humming right behind the walls of your own home? Thanks so much for joining me on this explainer, and keep questioning how our incredible world is wired.